שלום לכולם, בוקר טוב. אני ביקשתי מצחי שיאפשר לי להציג את יוחאי מגן. זה לא סתם כך. אז אנחנו כולנו קצת ציניים ודברים כאלה, אבל בכל זאת אני חושב שאני רואה את זה בתור אירוע מרגש משתי סיבות שמתחברות ביניהם. אחת היא שאנחנו מחדשים עכשיו את העונה של הסמינרים וכל הבלגן שקורה מסביב וכל באמת המצב, ושיוחאי זכה לעשות את זה, לפתוח את עונת הסמינרים שלנו, ואני מציג את זה מכיוון שיש לי קשר אישי אליו. אז בדרך כלל יש לנו סטודנט שלנו שמסיים כאן דוקטורט, אז אנחנו רואים את זה בתור איזה בר מצווה כזאת, ובא מתחיל לספר את זה בתור איזה שבוע של בר מצווה. אז זה מין בר מצווה כזאת. עכשיו, אני החפצתי את יוחאי בתור תלמיד, מכיוון שגידי לקח אותו, למד כאן את הבוגר, וגידי לקח אותו שהיה בשנה ג', נכון? אתה זוכר או לא זוכר? שנה ב', עוד יותר גרוע. בשנה ב' כבר גידי התלבש אליו, ואז אמרתי, זהו, זה עקוד, הגיאוכימיה הוא כבר לא יגיע, נלך לכיוון הזה שגידי מתעסק איתו, אז באמת, גידי טיפח אותו כבר משנה ב', ואחר כך הוא עבר לאוניברסיטת תל אביב, נכון? עבדתי עם גידי עם אלון, וזהו. עכשיו, הקשר האישי הוא שבדיוק לפני 20 שנה, אל תגיד בין כמה אתה היית, אני עבדתי בהימאליה ביחד עם יוחאי, והראיתי לו שמה, ולילדים האחרים שלנו היה טיול משפחות, 4 משפחות, 6 מבוגרים, 12 ילדים, ועמדנו שם מול הערים, והתחלתי להסביר מה זה קמטים ומה זה גרניטים, מה שזה. אף אחד לא הקשיב כמובן, אבל בסופו של דבר הוא הגיע לכאן. בהצלחה.
תודה אמרתי. אני אגיד כמה דברים בקטע המקצועי. אז נמשוך את זה עוד קצת. אז יוחאי עשה פה תואר ראשון, עשה מדעי המחשב וגיאולוגיה, ותוך כדי, כמו שמוטי אמר, התחיל לעבוד עם גידי ולהיכנס לעולם של גיאופיזיקה ואינסר, שעל זה הוא גם מדבר היום. עשה תואר שני ודוקטורט בתל אביב, עבד יחד עם גידי, אלון זיו, ובהמשך גם אסף ענבל, והוא יוצא בקרוב, עוד חודש ככה, לפוסט בסקריקס, בסן דייגו, לעבוד עם אליס גבריאל, ששם הזה כנראה לא אומר לכם יותר מדי, אבל עם הסייסמולוגים המובילים בעולם, גם מהצעירים יותר בעולם, אם תסתכלו עכשיו ב-EGU על כל המושבים של סייסמולוגיה, היא קונבינר או קו-קונבינר בערך על כולם. הוא מוצא מקום ממש טוב, ונושאים ממש מעניינים לעבוד עליהם, והוא הציג לנו עם ההרצאה הדוקטורט שלו, גם סייסמולוגיה, גם גיאודזיה, שילוב של אינסר ו-GPS. מתי תאוצה? פחות.
תודה. אני אעבור לאנגלית. So today I'm going to talk about earthquake slip inversion, and we will try to address the non-uniqueness of those models. We will do it through the lens of 2 recent earthquake sequences. The first will be from California, the 2019 Ridgecrest earthquake, and the second will be the devastating recent 2023 Turkish earthquake. We will start by talking about the motivation. What is the non-uniqueness of the inverse problem? We will move to introduce maybe the prime data set that we're going to use, which would be interferometric synthetic aperture radar, or INSAR. And then I will explain what earthquake slip inversion are, and specifically geodetic slip inversion, which is the specific inversion that I'm doing. And then we will go to the 2 case studies. So what is the non-uniqueness problem of the slip inversion models? In slip inversion models, we're trying to model source parameter of earthquakes, specifically the slip distribution of earthquake, and we're doing that by inverting data that we're gathering from Earth surface. And the problem is that when you modeling slip along fault, many slip models can explain similarly well the data that we're gathering on Earth surface. And here is an example from the Ridgecrest earthquake. I'm showing you 8 different slip models, and many more of them exist in the literature. And the key point is that all of them using approximately the same data set, so definitely INSAR and GNSS and some additional data sets, and all of them explain data similarly well. They do share one characteristic. The magnitude of the earthquake is the same in all of them, but apart from this, they're pretty different. The center of mass of the slip distribution is different in different models, over here and over here in our model. The maximum slip is different. They're pretty different. We will try to suggest a few methods in order to reduce this non-uniqueness. So our prime data set will be sub-interferometry. This is a remote sensing technique in order to retrieve back the displacement field of Earth, in our case of earthquakes. And we gather this data from SAR satellite. SAR satellites are orbiting Earth and imaging Earth with radio wave length images. And if we have some displacement event between two images, the distance that the wave is traveling between the satellite and the ground is different in the two images. This different distance is reflected in the phase difference between the two received waves in the satellite, and we can create a phase different map from two images, two sub-images. The phase different map look as so. This is the phase different map of the Ridgecrest earthquake. So this is not yet a displacement, just phase difference, where red to red color mean 2 pi phase difference. And we can transfer this phase different map to displacement map by a procedure called unwrapping. We're essentially assuming a very reasonable assumption that the displacement very far from the fault is 0, and then we're propagating through the image and summing up those phase differences and ending up with the following map. This is a displacement map in the line of sight of the satellite. This map are showing the changes in the distance between the satellite and the ground due to the Ridgecrest earthquake. So in earthquake slip inversion, we're trying to retrieve back the slip distribution of the earthquake. And here is a synthetic example for earthquake slip inversion. We can imagine some imaginary fault and imagine some slip distribution on this fault. And we can calculate the elastic kernel of this fault, or this slip distribution. The elastic kernel is telling us what will be effect of the slip on each point on the fault, on each pixel in the image. From the elastic kernel, we can calculate synthetic data, and then we can inverse our elastic kernel and apply it to our data to get back our slip distribution. Of course, when we calculate the data and inverting it with the same elastic kernel, we're getting a perfect slip distribution. We're ending up with the slip distribution that we started with. But the real world don't work like this. We have some error in our data. And here we're adding a small amount of error to our data. And then when we are applying the inverse of the elastic kernel, we're applying it also on the errors. And the errors from the data are mapped to the slip distribution. And we are ending up with a slip distribution which is pretty far from the slip distribution that we started with. Here are two approaches to address this problem. The first approach, which is a pretty straightforward approach, is to add some independent observation on the displacement field. So SAR satellites are flying both from south to north and from north to south, and imaging the Earth in slightly different geometries, so having slightly different views on the displacement field. So we can add those two geometries, two images, to our inversion, and we're essentially adding constraint to our inversion, and we're getting a bit closer slip distribution to the initial slip distribution. We can add some additional data set that we will see later in the talk. Another approach that could be taken for constraining the slip distribution is to apply some smoothing constraint on the slip distribution. And we're doing that by applying or by constraining the gradient of the slip to be 0 up to some smoothing constraint. And following doing that, we're getting slip distribution, which is very, very close to the slip distribution that we started with. But we need to remember that by doing so, we're taking an assumption that slip distribution on fault is smooth. An assumption that we will see is not necessarily true. So let's go to our case study. Our first case study will be the Ridgecrest earthquake sequence, where we will talk both on the co-seismic and post-seismic period of these events. And this event was composed out of a foreshock and a main shock. Foreshock was a magnitude 6.4 earthquake, and 34 hours later we had the main shock, a 7.1 magnitude earthquake. They both occurred in the Eastern California shear zone, which is a part of the tectonic border between the North American plate and the Pacific plate. And when we're looking on the main shock, here we're looking on the aftershock sequence, or the seismicity following the main shock. And we can see from the seismicity pattern and from the displacement from GNSS station, those are the orange arrow, that the main shock probably ruptured only or mostly on a north-west striking fault, the right lateral motion. But when we're looking on the foreshock, we're getting this very intriguing seismicity pattern. So these black dots are the aftershock occurring between the foreshock and the main shock in the 34-hour interval, and we're getting this perpendicular pattern, and not from the seismicity pattern, not from the moment tensor solution, and not from the displacement of the GNSS. We can tell which one of the fault has been ruptured during the foreshock. We will try to resolve a distinct slip solution for the two events, and by doing so, deciding which one of the fault has been ruptured. So here is the insert data for this event, and we have, as I mentioned, two images, one in the ascending track and one in the descending track. But we have one major problem with this data set. Here to the left, we can see the repeat pass time of Sentinel-1, the satellite that we took the data from. And we can see the satellite had a pass above the earthquake location few hours before the foreshock, and the second time he passed over the location was few days following the main shock. So those two images contain the superposition of displacement of the two events. So this data alone will not help us in order to distinctly solve for the two events. Luckily, we have some other method, and here I'm presenting pixel offset tracking data, which is out of optical imagery, but we can do that also from SAR imagery, which we will see in the Turkey case. But also the very large satellites are taking very high resolution imaging of Earth didn't pass above the earthquake location between the two events. And the only constellation to my knowledge that did pass is the Planet Lab constellation. It's a constellation of a microsatellite with more than 100 satellites in orbit, aiming to image the Earth, every point on Earth every 24 hours. So this constellation took an image of the earthquake location between the two events, the foreshock and the main shock, and we can calculate the pixel offset tracking, the method that track the movement of pixel in images and retrieve back the displacement field, the horizontal displacement field. In this case, the lower two images are for the main shock, and the upper two images are for the foreshock. Well, this is the north-south component of the displacement field, and this is the east-west component of the displacement field. So we got a distinct view of the displacement field of the two events. We now can take our data, the optical offset, the insert data and additionally the GPS or GNSS data, and we can put them all into our data vector, calculate the elastic kernel, and apply the inverse to the data to get a sleep distribution along the fault. This will be our fault, and we can see that the discretization of the fault, at least it's not uniform and it's not regular, and this is because we are suggesting a new method in order to discretize the fault plane and sample the data. This method aims to improve in resolving a distinct solution, and this is a reminder from the introduction that the error in the data are mapped to our model through the generalized inverse, through the elastic kernel. And we generally calculating this generalized inverse via singular value decomposition, and without getting into too much technical details, the errors in the data are multiplied by the inverse of the singular values of the SVD to model errors. So having a very small singular value can make small errors in the data to become very large errors in the model. So we suggest a method in order to optimize the discretization of the fault and the data that promise that those singular values will be sufficiently large. So here is our sleep distribution, where the lower two images are for the main shock, and the upper two images are for the foreshock. And maybe not surprisingly, the image that emerged for the main shock is that 98% of the moment is released on the northwest striking fault, on this fault, those faults. Where the image for the foreshock is more interesting. The moment budget is divided between three distinct asperities. One to the west of the co-seismic of the main shock, one to the east of the co-seismic of the main shock, and asperity number 2, which is located on the northwest striking fault, so on the same fault as the main shock. This can very nicely explain this perpendicular seismicity pattern, and additionally we can see that this asperity 2 has been ruptured twice. One during the foreshock, and the second time during the main shock, only in 34-hour interval. This implies on a very fast healing process of the fault. We will now move to talk about the post-seismic signature of this event, where here in the middle panel, or in middle two panels, we're seeing the time series of the GNSS station near the fault trace. So GNSS station record the displacement field regularly up to 1 Hertz, but in this case we're looking on a daily location of the GNSS station. And the green color represents the post-seismic signal. And what we can see is that the post-seismic signal is just a fraction of the co-seismic signal. So if the co-seismic signal we're talking about tens of centimeters to meters, the post-seismic signal is just few centimeters. To the left we can see the post-seismic signal of the entire geodetic network of California, and we can see that in general it's agree with right lateral motion on the northwest striking fault. So we're dealing with a very small displacement which are hard to detect, and they are even harder to detect in our case with traditional interferometry or INSAR. And this is because when we're talking about transform fault or side slip faults that are subparallel to the north-south, we need to understand that south satellites are orbiting Earth around the poles, so from north to south or south to north, and looking to the right. So they are sensitive mostly to the up-down component of the displacement field, and secondly to the east-west component of the displacement field. And indeed, if we are calculating the unit vector on the line of sight, we can see only 2% of the unit vector is due to the north-south component of the displacement field. So when we have a strike slip fault that is sub-parallel to the flight direction of the satellite, to north-south, we essentially, it's very hard to view it with traditional interferometry when the signal is very small. In order to mitigate that, we will use a new interferometry scheme. This scheme taking advantage of Sentinel-1 TOPS observation mode. In this observation mode, the satellite is observing Earth in consecutive bursts, where each 2 consecutive bursts are overlapped by 10%. This 10% creates 2 kilometer wide strips, which viewed twice in each satellite pass, one in a forward-looking geometry and one in a backward-looking geometry. So we have 4 independent views of the ground in each 2 images, and we can apply the following scheme. We will take the interferogram of the forward-looking and the backward-looking to get 2 interferograms in the line of sight, and then we can take the interferogram of the interferogram, cancel the line of sight component, and stay only with the flight direction component. And before jumping into the post-seismic signal, I want to show you the importance of the flight direction parallel component of the displacement field, and we will do so by showing the co-seismic signature as it's viewed by the burst overlap interferometry. So to the left we see again the traditional line of sight interferometry, or INSAR, in the ascending track. In the middle part we see the burst overlap interferometry in the ascending track. So we have this 2 kilometer wide data separated by 18 kilometers of no data, and the displacement showed is the displacement in the flight direction of the satellite, so positive in the flight direction, like the colored arrow, and to the right we can compare those 2 data sets. We're showing profile along those bursts in the 2 data sets. And we can see that we have some meaningful displacement, which means displacement above the noise level in the burst overlap interferometry very far from the fault, in B6 and B0, and even in B7 over here, which is more than 60 kilometers away from the fault tip. And when we're looking on the line of sight interferometry, we're going below the noise level, very close to the fault trace. Already in B5, which is over here, we can see that we do not have a meaningful displacement signal. Also, when we're looking on the bursts that crossing the fault, the burst overlap interferometry is showing a very classical view of displacement perpendicular to strike slip fault. This is the gray line, and it's showing more than 170 centimeters of offset between the 2 sides of the fault, where the line of sight interferometry is showing only 90 centimeters of displacement between the 2 sides of the fault. So the flight parallel component of the displacement field is the most important component in this case. So now we can move to see the post-seismic signal of the displacement field. And here I'm showing you the post-seismic signal in the first 5 months following the earthquake, where this is done over many interferograms. In the image before, we saw 1 interferogram. Here it's calculated over many interferograms and time series analysis that I will not get into. And we have 3 images, 1 line of sight interferometry of the ascending track, 1 line of sight interferometry of the descending track, and 1 burst overlap interferometry of the ascending track. And first of all, in contradicting what I said in the previous slide, we can see the strongest displacement is in the line of sight near the fault trace in places of fault geometry complexity. This is probably because the stresses due to the co-seismic slip following a large earthquake in a region of fault geometry complexity are very high, and we're probably seeing some poroelastic relaxation of the shallower crust, which is impacting mostly the vertical component of the displacement field and showed in the line of sight interferometry. We can see also this affecting the profile, seen in panel D, where we have an offset in the red line, which is the descending track, but we are not seeing the offset in the burst overlap interferometry, which means the displacement is probably in the vertical component of the displacement field. Additionally, we can see pretty strong displacement of more than 4 centimeters of the fault trace in burst overlap B4, which is okay to deal. This displacement can be viewed also in the line of sight interferometry for a few centimeters, and it's actually most strongly not over B4, but over this profile, AA prime, where we can see a significant displacement of the co-seismically active faults. We can also compare our burst overlap interferometry data to the GNSS network or GPS network around the fault, where we projected those displacement to the flight direction of the satellite. And this is, first of all, very reassuring that we did our processing right, because they have excellent agreement between the two data sets, where the GNSS data is available, but also the very sparse nature of the GNSS geodetic network, making them completely miss the significant deformation of the fault trace. This deformation is also visible in burst B5, so more than 15 kilometers away from the fault tip. We now can compare the core and post-seismic displacement as it's viewed in the burst overlap interferometry. And here in those profiles, we're keeping a constant ratio between the post-seismic and post-seismic signals of 1 to 20. And we can see that under those ratio, we're moving from the post-seismic slip to be larger across the fault trace to the post-seismic signature to be larger of the fault trace. And when we're calculating the ratio of the post-seismic displacement out of the entire displacement of this event, core and post-seismic, we're getting that across the fault trace, the post-seismic signature is accounting for only 1.5% of the displacement, while of the fault trace is accounting for more than 10% of the displacement. So something is happening to the northeast of the fault tip. We can also look on the temporal evolution of the displacement. And here we're looking on the relative motion of the burst overlap interferometry. So we're comparing the motion in the red rectangle over here to the motion in the red rectangle from the other side of the fault. And those are the gray dots in those 3 panels, where we're comparing them to the GNSS data when they are available. And we, again, can reassure that our processing was right, and there is a very good agreement between the 2 data sets. But we didn't have GNSS data to the northeast of the displacement field. So these time series will not be available without the burst overlap interferometry. And we can fit a logarithmic decaying function to those curves and get that the displacement is decaying faster to the northeast of the fault tip. We can now compare our displacement to the seismicity. And here are the seismicity sequence that we saw in the first slide of those earthquakes. And before that, we need to add some additional information. And this is that the earthquake rupture sees to the north at the coastal geothermal area. This is an active volcanic area with increased heat flow and pretty shallow transition between ductile to brittle deformation style at about 4 kilometer depth. And when we're looking on the seismicity as a function of COSO, we can see that the seismicity is decaying faster as we're getting closer to COSO. We can also put some number to this observation, and we can fit to the seismicity a logarithmic decaying function, and this logarithmic decaying function is characterized by characteristic decay time, capital T, and we can see again that the decay of the seismicity getting faster as we're getting away from this volcanic area. And additionally, we can compare now, because we fitted the same function to the displacement to the seismicity, we can compare the characteristic decay time of the deformation and the seismicity, and get that we have linear dependencies between the two decay times. So we're getting that the decay time of both the seismicity and the displacement is related to the mechanical properties of the crust. We can finally try to suggest some explanation to this observation, and we will do this by suggesting very simplistic slip model for the post-seismic of the Ridgecrest earthquake, and this will consider some deep slip along the co-seismically active fault. So co-seismic strikes fault usually rupture the shallower part between 0 to 14 kilometers of the crust, and this is increased significantly the stresses on the lower section of the crust, which is usually reacting by some post-seismic slip. And in addition to this post-seismic slip, we will add some off-fault slip along the normal fault to the northeast of the fault tip. And why normal fault? Because the coastal volcanic area is part of a releasing band between the Ridgecrest earthquake fault and the Owens Valley faults to the north. And we can see that when we suggesting this very simplistic model to consider only 5 very simple faults, we succeed to fit very well the burst overlap interferometry data, and pretty well the GNSS data. The INSAR data, we can fit the general pattern, but of course not the high deformation we saw near the fault race, which is related to pore elastic relaxation. We will now move to talk about the Turkish earthquake sequence, where this was a very devastating earthquake, which all of you probably remember, more than 60,000 deaths, and it's occurred along the East Anatolian fault. The main shock was a magnitude 7-point earthquake that ruptured all through the southern section of the East Anatolian fault, a magnitude 7.8 earthquake. And the second one, which I'm not calling an aftershock because they are very close in magnitude, was an earthquake rupture through the Soju fault, which is a splay fault to the East Anatolian fault. Those two faults are part of the tectonic border between the Arabian plate and the Anatolian block. The Arabian plate is moving to the north, and together with the Euro-Asian plate is squeezing the Anatolian block to the west. This creates a left lateral motion of about 1 centimeter per year along the East Anatolian fault. In order to resolve the slip distribution of those events, we will use two SAR satellites. We can see the footprint of the images over here, and the two satellites are, the first are the same as Ridgecrest, will be Sentinel-1 from the European Space Agency, and the second one will be ALOS-2 data out of the Japanese Space Agency. And luckily, like in the Ridgecrest case, all of those data sets are containing the superposition of the two earthquakes. In that case, only 8 hours divided between the two events. So, to my knowledge, none of the satellites in the sky pass above the location between the two events. So we essentially will solve for the two events simultaneously as one event. And why we even use two satellites? Here I'm presenting the line of sight interferometry or INSAR of the two events, and we can see that near the fault trace we have no data. This is because there was a very significant deformation. We will see it reach few meters of displacement near the fault trace, and this significant deformation causing decorrelation, which means that we cannot retrieve the phase, the INSAR phase, reliably, and we have no data near the fault trace. This will make solving for the shallower part of the fault very difficult. So to mitigate that, we essentially added an additional data set, the AOS2 data set. The AOS satellite is using longer wavelength data, and longer wavelengths are less sensitive to decorrelation, and indeed we can see that we're reaching almost to the fault trace, so we have much more additional information in that case. So this will be the line of sight data that we will use in our inversion. And additionally, we will use pixel offset tracking, but now of SAR data, not of optical data. So the displacement will not be north-south, east-west component, will be flight parallel and flight perpendicular component. In the bottom row, we can see the range offset, or the offset perpendicular to the satellite flight direction. And we can see that we get a very nice result in places where the fault to satellite geometry is optimal, like on the Surgery fault, where we get essentially the entire deformation. We're getting more than 8 meters of offset between the two sides of the fault. In the upper three panels, we see the displacement in the satellite flight direction, and we can see immediately it's much more noisy than the lower row. This is because the raw Sentinel-1 pixel size is 12 by 2 meters in favor of the range direction, and the accuracy of this method is about 10% of the pixel size. So, of course, we will get much more noisy result in the azimuth direction, the flight direction of the satellite. So we can essentially take from this data set only the places that the fault to satellite geometry is optimal and the displacement is sufficiently high. So in order to supplement this data set, we can of course use our burst overlap interferometry data. And this is the burst overlap interferometry data of the two Turkish earthquakes. And we need to remember that this is the same component.
What is A116, E021? What are
those? Those just A is for ascending and D is for descending. So the orbits of the satellite, and those are the names of the tracks. So naming the tracks of the satellite around the Earth.
So the different patterns that you showed previously were what?
Well,
A116,
different tracks. So
different
tracks. They're also different time. Those two are ascending tracks, so they are both flying from south to north, but they overlap by about also 10%, and they're adjacent to another. You can see that this region we see in the two images, but in this image they show us more.
So why is it descending on the A014 and descend and then uplift on D021? Why are the colors inverted?
Those displacements are completely horizontal, no uplift and no subsidence.
Why is the sign different?
The sign is because it's positive in the flight direction of the satellite. Here, this is an ascending track. It's just convention, okay? This is an ascending track. The satellite is flying from south to north, so it's positive in the satellite flight direction. And here is a descending track. The satellite is flying from north to south, so it's positive in the satellite flight direction. And it's looking to the right, and here it's looking to the right, so it's positive in the look direction, and here it's again looking to the right, and it's positive in the look direction.
Thanks.
Sorry if I didn't explain thoroughly. So this is the same. This is positive in the flight direction because you have, so here you again have a different sign, positive and negative. And this is show us the same component of the displacement field as the noisy data that we saw earlier. We can compare those two data sets, and we need to understand that they were calculated completely differently. This is by tracking the offsetting pixel, and this is an interferometric method. And indeed, we can see that the interferometric method is much more accurate, where we have much more noise in the azimuth offset. And we will now suggest a method in order to merge those two data sets into one data set. The new data set will have the spatial coverage of the azimuth offset and will approach the accuracy of the burst overlap interferometry. This will be done via a Kalman filtering approach, which I will not get into the detail of the approach, and will just jump to show you the final result. So this is the merged data sets, and you can see it's much cleaner. And we can also calculate the residual, which means the azimuth offset minus the merged data set, or the filtered data set. And we're getting that we stay with noise alone. So satisfying result. Another satisfying result is, which needs a bit of explanation before. We can see that the hypocenter of the first event, the magnitude 7-point event is here, which is not on the sanatorium fault, is on this branch. So the magnitude 7-point event started on an off-fault branch of the sanatorium fault, propagate into the sanatorium fault, and then bilaterally propagate along the sanatorium fault. And when we're looking on profile that crosses this fault, the azimuth offset essentially do not show us anything. But when we're looking on the burst overlap interferometry, we have a very nice offset on this fault of about 1.5 meters. And following the merging or the filtering of the data, we're getting the offset on this fault even on profiles that are not co-located with burst overlap interferometry data. So we succeed to retrieve the offset on this fault. Finally, we can take all the data sets and put them into our data vector and invert them back to the slip distribution. And just a reminder that we are applying a smoothing on our solution, but this comes at a price that we lose information, and we're assuming that the slip should be smooth, an assumption that is not necessarily true. It's even believed to not be true for pretty long. Before we had satellite imagery and etc., we imagined that slip distribution should follow the aftershock distribution along the fault. Essentially, we expect that aftershock will occur in places that experience stress increase due to co-seismic slip. So the slip should wrap around the aftershock location. And aftershock distribution along fault following earthquake is not smooth. So the slip also should not be smooth. So we are suggesting a new method in order to decide on this smoothing. The most common approach that is taken is to look on this solid curve, which is comparing the roughness of the fault, of the slip, against the misfit of the model, and taking the smoothest solution possible that do not hurt significantly the misfit. We suggest to look on a new parameter, which we named the aftershock gradient index. This is an approximation of the stress increase on the aftershocks, and it's done by summing the gradient of the slip in each aftershock location. And we suggest to take the smoothness that is the highest aftershock gradient index, the smoothest possible without hurting the aftershock gradient index significantly. So here is our slip distribution, and we can see that over here that the aftershock are very nicely wrapping the high slipping area as we would expect. And to the left we can see more closely the slip distribution, where here is the slip distribution of the Sorju fault, where the peak slip is on the Sorju fault with so the weaker earthquake produced the maximum slip of more than 12 meters. And the slip generally on the Sorju fault distribute regularly with maximum slip and decaying toward the edges of the fault. And this is the slip distribution along the Eastern Anatolian fault, and we can look on it a bit more closely also. And so this is the slip distribution, and here is the average slip along the fault as a function of distance along the strike. And we can see that the slip is divided to three distinct patches: 1, 2, 3, 1, 2, 3, and those patches are in excellent agreement with a previous mapping of the Eastern Anatolian fault. So those are a previous map section of the fault, which are divided by releasing and restricting bands. So the geological structure of the Eastern Anatolian fault is also constraining the slip distribution during a large earthquake. And I will finish with showing you a recent result. This is the 3-month post-seismic signal of the two Turkish earthquake. And here to the left, to the right, you can see the post-seismic offset along the core and post-seismic offset along the Eastern Anatolian fault. And we can see again that the post-seismic offset is following those three segments. And we can see also that the post-seismic following those segments, 1, 2, 3, where we have a creep to the east of the fault and a very significant post-seismic signature to the west of the fault. I will finish with showing the summary, and we'll be happy to take questions.
Great, thanks. Very interesting talk. Yeah, questions?
Thanks for the interesting talk. I have a question about the uniqueness issue. So
Sure.
we use multiple data sets.
Mm-hmm.
And do you use them, you basically prescribe all the different slips on different data sets in large metrics, observation metrics together? If so, it seems to me that it's more like an averaging than something that causes the uniqueness issue. You reduce noise, but is it really?
Adding data sets?
Yeah, is it really affecting uniqueness or just reducing noise?
It's not depending on adding data sets, it depends on adding independent view of the displacement field. So as I said, line of sight interferometry has if the displacement field is a 3D displacement field, and the line of sight interferometry, one image has only one-dimensional look on this displacement field. Okay, so adding independent views on this displacement field, adding constraint to the inversion.
In the post-seismic displacement modeling of the Ridgecrest earthquake, can you go back? The last slide, I think, before the Turkish earthquake. Yeah, this one. How is this? Your model is the red one, right?
Mm.
So what did you model exactly when you? What physics went into modeling this? Or?
So it's a very simplistic model. It's composed of Okada's dislocations. So we have 5 dislocations representing the deep slip under the coseismic reactive fault, an additional dislocation representing the off-fault sleep, and this is a forward model. So I just prescribe the amount of sleep.
So the off-fault sleep is represented by dislocation,
Mm-hmm.
so localized.
Mm-hmm. Yeah.
Thanks, very interesting.
Anyone else? I have a question about the geometry, because from what I got, this is the one thing that you don't really solve for, right?
The geometry of the fault.
Of the fault, yeah.
Not exact. So this Anatolian fault geometry is known. Also Suju fault.
Not only the geometry, but also the discretization of the, the model space of the patches.
So I do solve for it via the condition number optimization approach. Okay? So the fault geometry or the fault plane is discretized in a manner that promise the singular values of the inversion to be sufficiently high. So the inversion will be stable.
Mm-hmm. Also, can you go back to the geometry of the California Ridgecrest? So all these little angles and bends are something that's known.
So we there's few methods from offset tracking. The Turkish example is a better one because I have better data for those. But when you have an offset tracking like those, you can, and that's actually what I did. You can easily track the stripe of the fault. So the fault is just running between the red and blue over here. This is how I map the fault. The dip is a bit more complicated, but if you have many aftershock, the aftershock are following the dip of the fault. Okay. This is how we usually decide on the dip of the fault. Or in the case of the East Anatolian fault, is known that it's vertical fault. Mm-hmm.
About the last slide of the Turkish earthquake, the one with the inversion of the slip down to 25 kilometers. So what is the depth of the Moho? Down to 20 kilometers. So this is what you expected. You'd get that you'd get slip down to 20 kilometers.
First of all, the Soju fault is dipping about 70 degrees. So this is not 20 kilometers into the crust. Okay, over here talking. And I'm not sure about the Mohu depth, but yeah, you probably, it's worth checking if those are reliable sleep solution. But they also probably do not affect significantly the solution.
Yeah, I'm interested I'm interested from the question of whether you can get these co-seismic slips in the ductile regime. It's been seen. I was just interested in seeing again.
You can.
Nadia Lapusta.
So So those specific Okada's equation are assuming elasticity. You need to change the equation in calculating the elastic kernel to solve for ductile C.
Well, probably on this time scale you don't have that.
Yeah. People are solving for deeper section of the fault, definitely in subduction zone.